It's at this point that I like to discuss the difference between vaporization and boiling. So, vaporization occurs when molecules at the surface of a liquid have enough energy to vaporize or escape. We see that with this image here. The molecules at the top of that liquid are overcoming their intermolecular forces and they're escaping. They're becoming gas molecules. Boiling is the temperature, so we can think of the system as having enough energy. The temperature at which the partial pressure, the vapor pressure associated with that liquid equals the atmospheric pressure. So, in order for water to boil, under normal conditions, the vapor pressure or partial pressure of the water would have to equal 1 atmosphere. A couple summers ago, I went to visit some friends who had moved to Aspen. And the main complaint was that it was very difficult to cook at the high altitudes. And it kind of perplexed me at first, and so I really sat down and thought about it. Why are cooking times longer when you go to high altitudes, when you're in Denver or Aspen on the top of a mountain? What's going on? So at those high altitudes, you're going to experience lower atmospheric pressure. That's what makes it harder to breathe as well. And as a result, water can achieve equilibrium. The vapor pressure of water equals the atmospheric pressure at a much lower temperature. You have lower boiling points. So typically we expect water to boil at 100 degrees Celsius. But when you're at the top of a high mountain, it might start boiling at 98 degrees Celsius or 97 or 99. Just depends on the atmospheric pressure. The consequence of this, so instead of boiling your pasta at 100 degrees Celsius, now you're quote unquote boiling your pasta at 97 or 98 degrees Celsius. You're boiling it at a lower temperature. Therefore, you're going to have to extend the cooking time. A lot of our discussion here has focused on water, boiling point of water, but if we're comparing different kinds of liquids, and we see that a liquid has stronger intermolecular forces, we would then predict that it would require more energy for the molecules to escape, and that liquid would have a higher boiling point. So, all 3 molecules are bent. You always want to start these problems by drawing your Lewis dot structures, identifying the correct molecular geometry, and then making an assessment about polarity. Since they're all bent, they're all going to be polar. There's going to be some kind of distortion of that electron cloud. Bent molecules are always polar, no exceptions. Once you've identified all 3 molecules as being polar, then you can list dipole-dipole as one of the intermolecular forces exhibited by this set of molecules. In addition, since they all have electrons, we're going to see London dispersion intermolecular forces with all 3 as well. Here we have oxygen directly attached to hydrogen, so we also have hydrogen bonding with the water molecule. Hydrogen bonding is the strongest of all of our intermolecular forces. So if I'm listing them in terms of increasing boiling point, so lowest boiling point to the highest boiling point, I'm going to put water as having the highest boiling point because it has the most intermolecular forces. And there's a correlation. The more intermolecular forces, the stronger intermolecular forces will result in higher boiling points. Now, it seems like there's a tie between the dihydrogen sulfide and the dihydrogen selenide. Let's think about this. So we're going to somehow have to make some kind of judgment on as to which one has more or like stronger forces. I'm looking at the dipole-dipole, and remember dipole-dipole relates back to electronegativity. So sulfur has an electronegativity value of 2.58, and for the selenium it's 2.55. Based off of that, the sulfur is a little bit more electronegative. So it's going to have a slightly larger dipole-dipole intermolecular force. However, I really want to emphasize the fact that it's just slightly larger. And this problem would be super difficult to do without these values here. So in the past, when I didn't have this information here, the conclusion usually was that the dihydrogen sulfide has the higher boiling point because its sulfur is more electronegative and its dipole-dipole intermolecular forces are greater. However, the difference is so small. It's only slightly larger in terms of its dipole-dipole, but the molecule with selenium in it has a bunch more mass, larger mass, significantly larger mass. And usually we think about it in terms of mass because they go hand in hand. If you have a larger mass, that means you're going to have more electrons, and that means you're going to have a greater London dispersion intermolecular force. So it's very, very common. Usually the London dispersion is analyzed just based off of mass. Alright, so therefore at the end of the day, and you can look up these values, and again, this is a discussion question. You need outside information, and I like to just have the students kind of think about it and argue a little bit about it. In this particular example, we're going to list H2SE as having a higher boiling point than H2S because in this case, the difference in the London dispersion forces, the London dispersion forces for H2SE are so much greater than the London dispersion forces for H2S that it kind of overtakes the slight difference in the electronegativity values and the dipole-dipole forces. Capillary action is a little bit trickier. We see capillary action with straws. And thermometers. Thermometers is a really good one. So there's a couple things going on. One is cohesive forces. Cohesive forces are intermolecular forces between like molecules. And then we have adhesive forces, which are intermolecular forces between different molecules. So in a graduated cylinder, when you try to measure the volume of some water or some liquid, you see that meniscus and what's going on there. So the adhesive force, which in that case would be the intermolecular force, I'm going to just write force, between the glass and the water is so great that it's making the water is sticking more to the sides of the glass than to other water molecules. And we're going to look at what's going on with the glass in an example problem just here in a bit. In this problem, we're asked to identify the compound with the higher boiling point. So we're going to want to look for the compound that exhibits stronger or more intermolecular forces. In letter A, I've drawn out both compounds. We have two non-polar compounds. And one trick or one thing to know is that carbon-hydrogen bonds are considered non-polar. Basically, if you're assigning vectors, if you're trying to think of the polarity of a molecule and you have a bunch of carbon-hydrogen bonds, just ignore them. Only worry about the heteroatoms. Only worry about the odd ones, like the oxygen and the bromines. Don't worry about carbon-hydrogen when you're doing your analysis. So right away, I'm just like, okay, everything's non-polar in these images. So due to the fact that everything's non-polar, we only have London dispersion forces in both of these compounds. Now, when it comes to London dispersion, there's two things we need to think about. We need to think about size and we need to think about shape. Both of these molecules have comparable shapes. We have a tetrahedral carbon here, and here we have two tetrahedral carbons. So not much going on with shape. So I'm going to give it to size. This ethane is a much larger compound. It's almost twice the size of this one. So I'm going to say that over here we have larger London dispersion because of the larger size, which means C2H6 would have the higher boiling point. Moving on to letter B, we have ethane again. And same analysis, just carbon and hydrogen, so right away nonpolar, nothing interesting there. Since it's just nonpolar, we just have London dispersion. So on this next one, the methanol, we have CH3, and then we have an O and an H. We're going to list it as polar. And there's a couple ways that I know it's polar. One, it's not very symmetrical looking. Secondly, I'm going to ignore all of this over here because it's just carbon-hydrogen bonds. Carbon-oxygen is interesting. So between carbon and oxygen, I'm going to predict a pull towards the oxygen. And between oxygen and hydrogen, I would also expect a pull or distortion of the electron cloud towards the oxygen. So both of those arrows are kind of pointing like up towards each other. So maybe there's some kind of net dipole that looks like that. Kind of just an estimate. If there was a tug of war, where would this molecule move? Where would the oxygen move? And I know it bothers people when I tell them, just ignore carbon, hydrogen. Carbon's it would just be such a tiny arrow if you wanted to draw it in. So remember, vectors also reflect the size of the pole. So that's why we just ignore them. Don't even bother drawing in those tiny arrows. However, at the end of the day, this is a polar molecule. So we can assign dipole-dipole, London dispersion, and we have H directly connected to the phone, F, O, or N. So we also have hydrogen bonding here. Methanol definitely takes it. It has a lot more intermolecular forces, a lot more going on, so it's going to have the higher boiling point. In 3C, we're asked to compare hydrobromic acid to hydrochloric acid. They both are polar molecules with the polarity of the hydrochloric acid being slightly greater because its electronegativity value is 3.0. So I'm going to list dipole-dipole as forces for both, but I'm going to make note that it's larger for the hydrochloric acid. They both have London dispersion intermolecular forces as well. And in terms of London dispersion, the hydrobromic acid is more than twice as large compared to the hydrochloric acid. It's 81 grams per mole. This guy's only 36.5 grams per mole. So the London dispersion forces are much larger. We saw an example earlier that was very similar to this. Sometimes dipole-dipole intermolecular forces make the difference in terms of analyzing boiling point or viscosity or whatnot. However, the electronegativity values of the atoms have to be different enough to overcome the difference in size. And here it's not. These are just really close, 2.8 and 3.0. So their dipole-dipole intermolecular forces are pretty comparable. However, they're very different in size. So the London dispersion force of hydrobromic acid is significantly larger, and therefore I would predict that hydrobromic acid has the higher boiling point. In letter 3D, we're asked to compare ethane, which is nonpolar and only exhibits London dispersion forces, to CH3Br, which, because of the bromine, is a polar molecule and exhibits dipole-dipole intermolecular forces as well. Therefore, CH3Br will exhibit the higher boiling point. In this problem, we're looking for the molecule with the higher vapor pressure. Higher vapor pressure is the one that's the indirect relationship, so we're looking for less intermolecular forces. Methane versus ammonia. So methane's nonpolar, therefore it will just exhibit London dispersion. Ammonia is polar. We have dipole-dipole intermolecular forces, London dispersion, and hydrogen bonding, because we have an H directly attached to the phone. Less going on with methane, therefore it will exhibit the higher vapor pressure. In letter B, we're asked to compare the methane to ethane. Ethane is also nonpolar, and so it just has London dispersion. However, in this case, the London dispersion will be larger due to the larger mass, due to the greater number of electrons. At the end of the day, the methane will once again have that higher vapor pressure. In our last example, we're asked to compare ethane to methanol. Methanol has a polar oxygen atom and therefore exhibits all three intermolecular forces. We see dipole-dipole, hydrogen bonding, and of course London dispersion. So much going on with methanol that we're going to predict that ethane, just because it doesn't have that much going on, will have higher vapor pressure. This first compound is the ethanol. It has an electronegative oxygen atom, and that causes ethanol to be polar. As a result, and as a result of the fact that there's a hydrogen directly bonded to oxygen, we can list all three intermolecular forces for the ethanol. The next compound is the dimethyl ether. It too is polar. We have an oxygen with a bent shape to it. So whenever you have something that's bent, it's typically, at least at this level of study, it's going to be polar. I'm going to list dipole-dipole as an intermolecular force due to the polarity. And we'll also have London dispersion. This compound has hydrogen. This compound has oxygen, but they're not directly connected. So there's no hydrogen bonding in dimethyl ether. Which compound has the higher boiling point? That's going to be the ethanol because it has more intermolecular forces. Remember, with boiling point, we see a direct relationship. Which compound has the higher vapor pressure? Vapor pressure is the one that goes in opposite directions. So a higher vapor pressure is going to be less or weaker intermolecular forces. So here the answer is going to be dimethyl ether. Here we were given the structure of glycerol, and we want to draw out the Lewis structure of acetone. It's a little bit tricky. We have two CH3 groups attached to a carbon, which is then attached to an oxygen. So that's what you see here. And then water is also part of this analysis. Water's polar because it's bent. And let's start with water. So therefore we can list dipole-dipole intermolecular forces, hydrogen bonding, and London dispersion. For the acetone, we have a trigonal planar carbon here in the middle. There's 3 electron groups. It's trigonal planar. However, the 3 electron groups are not the same. Oxygen is very electronegative, so we would expect some kind of distortion of the electron cloud towards the oxygen. So I'm going to say that acetone is polar and exhibits dipole-dipole intermolecular forces. We also need to include London dispersion on this list, but not hydrogen bonding, right? Because there's no hydrogen directly attached to the oxygen or nitrogen or fluorine. Glycerol, working backwards for some reasons. Glycerol is interesting. So we have an oxygen with a hydrogen here, and then we have another oxygen with a hydrogen and another oxygen with a hydrogen. So in glycerol, I have hydrogen bonding in 3 different locations. All of these oxygens are definitely going to make glycerol polar. Therefore, it's going to have dipole-dipole. And it's a pretty big molecule, so it's definitely going to have London dispersion. Which compound do we expect to be the most viscous? Well, it seems like water and glycerol both have the same list of intermolecular forces. However, the glycerol has greater London dispersion forces due to its greater size, and it's got 3 times as much hydrogen bonding going on as well. So I'm going to predict that glycerol is the most viscous because it has the strongest intermolecular forces. Acetone, on the other hand, doesn't have hydrogen bonding. Therefore, I'm going to list acetone as the least viscous of the 3 because it has less intermolecular forces. Part 7 asks us to look at surface tension and to compare acetone or water. I'm going to go with water because it exhibits hydrogen bonding. It has one more intermolecular force and a very strong intermolecular force at that, right? Hydrogen bonding is the strongest of all the intermolecular forces. And so water would have a greater surface tension because it exhibits hydrogen bonding, while acetone does not. Here we're looking at isomers. Isomers are compounds that have the same formula. These are both C17H16. They're both heptane, but they're connected in different ways. Now, since these compounds only contain carbon and hydrogen, we can describe them both as being nonpolar. Therefore, London dispersion will be the only intermolecular force exhibited by compound A and compound B. Now we have to make a judgment about which one will exhibit greater London dispersion forces. Well, they're the same compound. They have the same formula. So the masses are exactly the same. The number of electrons are exactly the same. So there won't be a difference in terms of size. However, the shapes are super different. Here we have this more linear structure. And students oftentimes get upset at me when I describe compound A as being linear. Yes, each one of these carbons are tetrahedral carbons. However, they're lined up. They're in a line. Whereas over here, again, we have tetrahedral carbons. But they're more clustered. So there's this carbon in the center with 4 carbons attached to it. And this cluster, this more spherical shape, results in hidden electrons. And I discussed this briefly in another video, but these electrons in the middle here, and maybe some of these electrons over here, since there's another carbon there, another methyl group, don't get to participate as readily or as easily in the temporary dipoles because they're hidden by the other electrons in the molecule. So these electrons on the outside get to do their thing and create those temporary dipoles. But these hidden electrons, not so much. Here we don't have any hidden electrons. All of the electrons are at the surface of the molecule. They're all in a position where they can interact with other molecules. So rule of thumb is that spherical or like more cluster-like compounds will have smaller London dispersion forces, all other factors being equal. So here we're going to have larger London dispersion since everything's more spread out, larger surface area, and as a result I would expect compound A to have the greater viscosity. So for this last problem, we're asked to explain why water exhibits a concave meniscus when it's in a glass tube. Mercury, on the other hand, exhibits a convex meniscus. What does this mean? It means that water prefers the glass over other water molecules. The adhesive forces between the glass and the water are greater than the cohesive forces between water molecules. Mercury, on the other hand, prefers to hang out with other mercury atoms. It doesn't want to interact with the glass. Why is that? Well, if we look at the structure of glass, it has ion dipole forces. We have calcium 2+, sodium ions. this is important because ion dipole forces are stronger even than dipole-dipole and hydrogen bonding. So therefore, water, since it has the hydrogen bonding, is going to feel comfortable in an environment with ions. Ions and water love each other. But mercury is a single atom and it's nonpolar. It only exhibits London dispersion forces. So it's not going to like being in a charged environment like this with the ion dipole forces. It just doesn't feel comfortable. And we can think of ions as being the most extreme example of polarity. A nonpolar atom doesn't feel comfortable interacting with the extreme polarity of the glass.